Hey YouTube, what is going on? I hope all is well. I apologize in advance. I've got the tree trimmers here doing some work, and boy oh boy are they going to work at the only time that I have time to do this with you guys. I apologize, bear with me, we're gonna get through this together, you and I. Alright, so I am probably not going to include this as part of the video build series for this amplifier. Mainly because 10 parts is a bit on the long side. There's probably close to 8 hours worth of content there. And we're kind of at the point where it's really not about building the amplifier anymore as much as it is just like fine-tuning it. And I can kind of explain that in a separate video, and a lot of these concepts are something that is really best described in separate videos anyway. What we're going to do today is just kind of make this a biasing video with a sound sample of this amplifier. I may chop this up and finish out part 10 with it, or call this part 10 just because it does have a sound sample of this amplifier. However, there's a problem. As good of a job as I did on this amplifier build, it still isn't right. I'm not 100% happy with it, even when it's biased properly. So there's some things I got to do to it that will make it complete and ready for market, that I go a little bit beyond the scope of just putting it in a build series. So for one, we need to establish whether or not we can even bias this thing to begin with. In the last video, 9.3, I think I mentioned that right now it's cold. I knew that it was cold because I measured the voltage across the cathode there. And you can do that across the cathode resistor, right? So you measure this voltage here across this point, and the amp's actually got to be on. That helps a lot, right? I mean, duh. So the amp's currently on, at least it better be. Yes, it is. And we measure that voltage going across the resistor there, and it's just now starting to conduct. You can see the voltage raising there. It's 10 volts, 11 volts, it'll go up to 12, and I think it'll settle at 13 volts here in a moment once it's actually up to operating range. 12 volts would be ideal, but I know that it's a little bit high. There it goes. It's at 13 volts now. I don't know if you can actually see that or not. I'll make it so you can. There you go. 13 volts. So I know that that's too high. The voltage drop across it is too high, meaning that the bias is too low or cold. I'm going to put a link in the doobly-doo, the description box, linking to Rob Robinette and how to bias amplifiers and his tube bias calculator. Great little tools. This is a cathode biased amp, not a fixed bias amp, so it doesn't have like an adjustable thing, and it doesn't have a negative, bias supply in it. This one is biased by that resistor right there. So in order to bias this amp, you have to get the right resistor in that position there. So how cold is too cold for a cathode biased amp? In general, with a cathode biased amp, you're trying to bias it to right about 100%, or as near 100% as you can get it. The problem with that is that generally you don't mess with the B+ or the HT voltage in order to do that. Right? So you got whatever your plate voltage is coming in, and then you adjust the bias with the resistor. Well, there's only a few values of resistors that are available for market that you can get for this position right here. I have 180 ohm in there currently on one of my other builds with the voltage that is currently, inside of the amp. That biases the amp very, very well. In this particular one, it's too cold. A different set of tubes in here, and it might do something completely different. So it is definitely not, a one-size-fits-all. Most amps just come with one that is close enough. And I would say 180 ohms is close enough. It makes it so the amp will function safely and with, without too many issues. However, that does not make it correct. That is not an excuse, I should say. So objectively, we need to find out if going to the next lowest value is possible. The next lowest value being 150 ohms. That's the next common available size that you can get for this type of resistor. So right now, 180 ohms. Will 150 ohms work? Don't know. Let's do some things to find out. So let's go ahead and turn off the amplifier, because there are some things that we can do to do this without going to a calculator online or something like that. one of those things is we need to measure what the value of the oh my god, if I could spit the fucking words out. The center tap to plate, or anode, if you want to call it that, whatever that resistance is. So what we're doing is the output transformer resistance method for biasing the amplifier. This is probably one of the more accurate ways to bias any guitar amplifier, but we just need to know a few points of data first. First of all, we need to know what the resistance between the center tap and the plate is of that side of the transformer. So we put a probe on where the center tap would be, which is that red wire there. It's the one that comes from the output transformer. And then one over to the brown and or the blue. So right now this one's reading 319 ohms. Earlier when I was checking this, it was reading out at 298. It's a little bit warmer now is what it is. So as the output transformer is hot or gets hotter or colder, it will change the resistance. So when it gets hotter, it will increase the resistance, and as it gets colder, it will actually reduce the resistance. So at room temperature, it might read, God, if I can get it to hold still, it might read, you know, 298 and then 333 respectively. That's what it was reading earlier before I was doing any work on this thing. Now that the amp is warmed up and has some heat in it, the transformer is reading 318 and 357 ohms. There is nothing wrong with that. That is completely normal. Write that number down. You can rely on that number for the life of this output transformer. And it's just a standard that you can go with. So right now it's just double checking. It's 319. Yep, 319 and 357. That's what we're going to say that those ohms are. So write that down. Brown is 319 and blue is 357 ohms. All right, now all we need to do is plug the amplifier back in. Remember, when you're doing that, to unplug the amplifier, don't be silly. Don't be, you know, if you're probing around in there with shit that you're not trying to get voltages from, make sure that the amplifier is either off and or that you've done all the due diligence to make sure you're not touching anything you're not supposed to be. So we're going to come out of resistance mode, and we're just going to go up to the highest DC voltage reading that it can come to, which is the 600 volts in this particular DMM's options. Now what we need is the cathode, or the voltage drop, excuse me, across each of those things. So same point, we're going to take the voltage and put it on the center tap, and then we're going to measure the voltage at the plate. So we've got a 10 volt drop here, and on this one here, we probably got something closer to 11. Okay, that is correct. So we got 10 volts dropped across this side of the transformer, and we've got 11 volts dropped across that side of the transformer. So how does that work? What do we do? Well, remember that resistance that we wrote down, right? So we're going to take the volts that we have as a voltage drop. So on this side here, we've got 10 volts. So for brown, we're going to write 10. And we're going to divide that by the ohms. So it was 319 ohms. It's 31 milliamps is what we're currently drawing. 31 is a little on the cold side. I'd say that 36 to 37 is probably ideal. So that's a little bit cold right now. Now what's the other side? So we take 11 volts and then we divide that by 357 ohms. And that equals 30 milliamps. So that side's definitely a little bit colder. So we're sitting at 30 and 31 respectively. So not too bad. It is, like I say, a little cold. But how cold? Well, let's find out. So if we go again over to the tube bias calc that Rob Robinette has, and we punch in some numbers, it'll kind of help us get an idea of how cold it really actually is. So what we need to do is establish what the plate to cathode voltage is. The plate to cathode voltage is from this point of the cathode, so not the ground side, but the actual bottom of the cathode of the tube. So we're going to take this probe here, it's still in the 600 volt mode, and then we're going to get the voltage to the plate. And in this case, it's 326 volts. And you can do it from both, and it should be the same for each one. 324 and 326. We'll call it 325 volts. So 325 volts is what our current voltage drop is. With 325 volts, if we punch all this data in onto the tube bias calculator, it's saying that our ideal at 95% is 35 milliamps, and our 100% max safe dissipation is 36.9. So we're looking for right around 36 milliamps to 35 milliamps, right in that range. 37 might be a little on the hot side. So where are we at? We're right now, we're at 30 and 31 respectively. We're at about 85% of bias for this cathode bias. A bit on the cold side. What does that do? It causes the amplifier to go into Class B mode. So it takes it from Class A. So a cathode biased amp only works in Class A mode when it's at idle, i.e. no input, nothing going on. It's just on. That's all it's doing, right? At that point, you bias it for 100%, but as you play, the bias is actually going to cool down. It's going to go from Class A to Class AB, and then quite likely, depending on how loud you turn the amp up, will bias down to Class B mode, or very, very, very close to it. It causes crossover distortion, and crossover distortion is just an ugly sounding kind of distortion where the AC signal that comes in, you know, the sine wave that it creates as it, you know, the signal goes in and then out, that sine wave that it creates starts to break apart and shift, and it causes kinks in the sine wave. And that comes, we hear it as distortion. It doesn't sound very good. So right now we're definitely too cold. So how do we raise it? Well, to raise it, we have to go to a lower value resistor right there. But is 150 ohms going to be too much? Well, that's what we need to figure out. So right now, I'm going to take this resistor here. It's just a 1K. Whoops. Whoops, whoops, whoops. Don't want to drop them in there, of course, but I'll get it out. It's all good. We're all right. It's okay. I didn't touch anything. I promise. So we're going to take a 1K resistor, and we're going to put it in there. Just across. This is a temporary thing here. We're just going to try to figure out what this is going to do for us, if it'll work or not. So we're just going to tack it in and determine whether or not that's going to do anything for us. This is going to be very ugly. I apologize. I'm just trying to do this quickly without getting my face in the shot. Okay. I need a little more of this. And if you wouldn't mind melting. There you go. Alright. There it is. I'm going to turn the iron off. My apologies, I'm all over the place. Okay, so now what is the ohms of that resistor? Let's find out exactly what those two add up to be. Should be around 150. It says it's 151 now. I don't know if you can read that. 151 ohms. So that's pretty close. That's the next standard value down without actually taking this one out and putting another one in. So we'll write that down. Things are going to change here though now. So with a 151 ohm resistor in there, things are going to change. So let's find out how that's going to change. So we're going to come back into the high voltage, you know, the 600 volts, and then we're going to plug in the amp, and we're going to turn it on. So it's going to change what our B plus value is, because now this tube should be conducting more. And as it conducts more, it's going to pull down, it's going to draw down the HT voltage. So before, I think we were at 350, something like that. I don't know if we took that voltage or not. Yeah, I think we did. I think it was like 351. Now it's 345. So it dropped about 5 or 6 volts there. All right. And I think at the plate, I think we measured it, it's 333. That's not bad. Okay, so what is our cathode to center tap voltage now? So now we have an 11 volt drop on this tube, and on this one here, I'll bet it's 12 volts. So now we have an 11 volt and a 12 volt drop respectively. And I'll bet the drop across this thing here has gone up to 12 volts, or down to 12. Hey, what do you know? Right at 12. That's pretty much what we're looking for. So it was 13 before, now it is 12. But what does that equal up to? So remember, it was 11 volts here, so it's 11 volts divided by 319 ohms, because that's what it was at the time, 34 milliamps. So we're not quite at 95%, we're just under 95%. And then the other one was 12 volts, and we divide that by 357 ohms, and we're at 33%. So we're sitting right about 95%. Very, very close, 94, 95%. That's a lot closer than we were. We could go lower, but we know now that a 150 ohm resistor will work in this amp, and we will not be biased over 100%. And I'm looking at the tubes now, and I can tell you that I don't see any red plates, so that's good. And I'm wearing a red shirt even, so we are in the safe zone right now. But as I mentioned, it does, depending on what you do, drop the voltage. So without that resistor there, when we were at 180 ohms, we were seeing about 351 volts here. Now we're at 344. So it drops the voltage down, which changes how these tubes react a little bit. Let's talk a little bit about some of these design limitations that I was mentioning in some of the other videos as to why it is not a great idea to be just a copy and paster and just take other amps that you know that you like and then just start building them with random bullshit. This output transformer is specifically for an 18-watt guitar amp. However, it was made to replicate a transformer made 60 some odd fucking years ago. And in so, it's producing a little bit more voltage, I think, than what was originally being created at that era. And if you look at the data sheets for an EL84, I'm speaking more in terms specifically to this amp here, okay? Not just broad spectrum here or whatnot, but EL84 tubes have a design limitation of 300 volts max on the plate and the screen grid. So the screen grid is that guy there that this guy connects to, that resistor that's kind of hanging out to the side there. That's going to the G2 screen grid. That one is designed to have no more than 300 volts on it, and the plate is designed to have no more than 300 volts on them. And as we know right now, they both have about 340 volts sitting on them. 320 on the grid, the G2 grid, which is the screen grid, sorry. That is not exactly good. What it does produce is a little more output, so we get a little more snot out of it. But it changes how that tube works. The design center, or the voltage that the tube was actually designed to work at, is 250 volts. So ideally, in a perfect world, we would only be supplying 250 volts to the plate of that tube and no more than 250 volts to the screen grid. The screen grid should always be just a little bit lower than the plate. Whether it's 5 volts, 10 volts, or 20 volts, that's up to you to decide, but it should not be the same voltage. It should be at least 5 volts lower or more. That's more of a safety thing, but whatever, we can go into that. That's another subject. But we are well over the limitation, and everybody talks about how EL84s and modern tubes can't handle, can't deal with all the stresses and stuff that these amps put on them. It's not the tube's fucking fault that guitar amp designers, time and time again, keep doing the same bullshit and designing amps, copying the freaking shit from years and years and years ago. I'm guilty of it too. I'm doing it right now, right? So I bought a transformer that puts too much voltage on the plates and grids of the EL84s. That is not the tube manufacturer's fault. They are making the tubes just as good as they need to be, and they do what they say they are supposed to do. I'm going to do something here real quick. I apologize. I'm going to bump things. So the only way around that is to try to lower the B+ voltage lower the B+ voltage. Ideally, that's what you would do. The problem is that to do that, there's only really two ways to do that. One is to use Zener diodes, and the second is to order a custom transformer that has a lower output voltage than, the standard current options that are available. So Zener diodes unfortunately produce heat when they're essentially wasting energy. In this case, I need to drop at least 40 volts Probably more like 50 volts if I want to get it to the you know, a more ideal range. And I did this off camera earlier. That's why some of the soldering spots on that cathode resistor are a little bit ugly. Sorry I was doing work without you. However, I needed to do it because I wanted to figure out for sure what the issue was, why this amp has a problem. The problem is, it works great, sounds pretty damn good, but it is suffering from the classic 18 watt fizz, or the 18 watt buzz. That is not necessarily just an 18 watt thing. It happens with any amp that is pushed to the fucking limits like this thing is. 18 watts are just a little more egregious with it, so it's a kind of a thing that they do, right? Vox amps are just as susceptible to it. It's just that they usually have a thinner guitar signal going in, and with a thinner signal, it has less propensity to expose itself as, you know, the swirl or fizz or whatnot. They also use lower grid stopper, or excuse me, grid leak values, which helps tune some of that out. A standard 18 watt uses 470K grid stoppers, or grid leak resistors, excuse me, for the power tubes, which really just allows that amp to spank the ever-living shit out of those EL84s. And in doing so, it really causes them to go into fizz land, because they're working very, very freaking hard. And especially with having too much voltage on the plate, it just makes that propensity a little bit higher. So I dropped this down with some Zeners to just under 300 volts. I think I had about 298 volts on the plate, and I had about 286 volts on the G2 grid, the screen grid. And 90% of the fizz went away. So the fizz is caused by the amount of voltage on the plate. I don't think it's necessarily just the bias shift. There still is a bias shift, and the bias shift is part of the problem. It is not the whole of the problem. I wish we could go into the you know, all the details and, you know, empirical data and all that jazz today to show my point, but that's for another video. The problem is that to drop that amount of voltage requires a lot of current draw through the Zener diode. To factor what that is, you take the Zener voltage, so let's say 12 volts, right? Well, you take that 12 volts and you divide it by the amount of current draw that is on that Zener. So if you have a 12 volt Zener and you divide it by the milliamp draw that's going through it, and I think in this amp here it's about 100 milliamps, so it would be drawing about 1.2 watts. Not too bad with a 12 volt drop, right? Well, we need to drop 50 volts in order for us to get it down into the safe zone, right? So let's imagine that now. So now we need to take 50 volts and divide that by 100 milliohms, and you get 5 watts. Well, the unfortunate thing is I don't have a 50 volt 5 watt Zener, but if I were to put a 50 volt 5 watt Zener in here, it would immediately burn up because we have met the, you know, the design limitation of it. We're pulling that entire 5 watts out. Can't do that. So I need to split the load up over 2 of them. So if you string Zeners, you know, along to add up to the total amount of voltage you need to drop, then you can spread that load over multiple Zeners, right? And it should equal less current on each one of them. That does work, but then you start coming up to a space, and you know, what do you do with all that extra heat type of thing? In my case, I'm not set up and I don't have the parts available to me right now to do that. I was able to do it long enough to test it to find out that it does work, but it is not a permanent solution. I think if you're drawing 5 watts worth of power through any amount of, you know, diodes in a string, you really should have diodes that are rated for twice that. So I need 10 amp diodes realistically to do it properly. And I would probably, just for the sake of, you know, safety and just keeping the heat down just a little bit, I would get a 20 watt diode and try to drop maybe all 40 volts or 50 volts in just one diode, as opposed to trying to use a string, mostly to save on space. Okay, enough of that. What we do know is that we can fix that problem also by using the Paul Ruby mod. Now the Paul Ruby mod deals with that situation by keeping the bias from shifting too far. So when you have this amp cranked to 11 and then you bust out your power cord galore, what it does is it actually sucks the bias down. So the bias goes from 100% down to, you know, probably closer to 50 or 60%, to be honest. I'll bet anything the cathode voltage drops up to, I shouldn't say drop, but goes up to 24 volts. So almost double the voltage, which means you drop half of that, you know, bias out. So you go from 100 volts or 100% bias down to 50% bias, kind of just by strumming the chords. That is one reason that you get the distortion that way, the fizz, the swirl, and all that jazz. Part two is that you get blocking distortion. Blocking distortion is where the electrons flow into the grid of the tube, and they sit there. And they sit there and charge up because it's actually charging up the coupling capacitors. And as the coupling capacitors charge up, they won't flow anymore. And that's what stops it, you know, the things from coming in. So you hit the power cord and it kind of goes, and then, right? It just pukes it out afterwards. And that's why you kind of hear it as like a suck. Like the volume will suck away and then it'll kind of swell back, just kind of like a bleh. But that is the blocking distortion that happens with tubes in general. It does not sound good, and when you're right on the verge of that blocking distortion, it really causes some havoc. One reason is that they use very low value grid stoppers on most amps of this type of design. I'm guilty of it too, although I do solve that problem by going with higher than typical values. What value is dependent upon the amp, not necessarily, it's not necessarily one size fits all. I start with 1.5Ks and I go up as high as is needed. This amp will probably end up with a much higher value than 1.5K. The grid leaks, there's not much you can do. I'm already at 270K, which is a fairly standard value. And then with the master volume kind of around it, it's actually a little bit lower. It's probably closer to 2K or 200K, which there's no point in trying to get it any lower. So if I were to go with 100K grid leak, it's really not going to help the problem much because it's going to take some of the gain away as well, which I don't want to get rid of the gain. I just want to get rid of the fizz. And the fizz is a result of the voltage on the tubes and the amount of bias shift. There are a couple other ways to stop the bias shift. One of them is to place a Zener diode that is reversed biased. What do they call it? It's reversed... I think it's reverse biased or whatever, but it's turned around the other way. So what it does is it keeps that cathode from dropping more than the Zener diode. So it locks it in. So if I'm sitting at 12 volts now, I would set it for say 13 or 14 volts, and it'll allow it to drop up to the 14 volts. At which point it will no longer drop anymore. It'll just hold it there, which helps kind of keep the bias from shifting too cold, although it does not stop the entirety of the fizz problem. Again, the fizz problem is part blocking distortion and part bias shift, okay? And then part, having way too much voltage on the plates of the tubes. So those three things are what creates the modern problem with these amps. Some amps don't display that problem, and others do. What does this amp sound like though? Let's do that. So I'm going to hit the record button here. I think I am recording. Yes, I am. I am going to pick up my untuned guitar. And I apologize that it's untuned. I just, I have my shop beaters and whatnot. So this amp right now is currently going into a Torpedo Captor X. I am using a stock IR that already exists in this Torpedo. I believe it is the one for the Hughes and Kettner Triaxis. It's just a greenback loaded 4x12. I like greenbacks, and it was the only one I found that had all greenbacks in it that sounded like this. So what are we listening for? I'm going to try to emphasize the swirl I'm talking about, the fizz. So you kind of hear that over the top of the signal. That is the swirl that they talk about in an 18-watt amp. So it's not super duper bad. It was way worse. It was way worse than that when this amp was biased a little bit colder. So when it was biased at 85%, it was definitely worse. That is with this amp dimed. I have the low cut set at about noon. Lowering the low cut or dropping it all the way out does kind of help a little bit. Again, I was talking about the blocking distortion. That's part of it. So since you reduce some of the low end coming in, it reduces some of that blocking distortion and it cleans it up a little bit, but not much. So you can just hear it sitting there. It's riding on the top. This is fixable. I can get rid of it. I can either drop the B plus and do it with that. I can use the Paul Ruby mod. I can use higher grid stopper values on the tubes, the plates, excuse me, of the grids of the output tubes. I can do those three things and that will get rid of it and turn it into a monster. That's what this amp basically sounds like with single coil pickups, mind you. Oh boy. Oh, try that again. So it's pretty mean, right? This thing is designed to do clean to mean, so if I roll down the volume a little bit, I get a little bit lower even. Lower even. All right, that's cool. That's all great and all. So sorry, the reverb that you are actually hearing is the reverb that is coming from the Torpedo Captor X. I just got to have a little bit. So let's see if we can clean that up a little bit and get rid of the fizz. So I'm taking the master volume and turning it down a little bit. I call that acceptable right there, but you can hear that it takes a little bit of the drive out of it. So yeah, it does work, but what does this amp do with clean levels? So let's turn this down into clean level land here. I'll turn that up there and see what we get. Let me go ahead and turn up the Captor X there. So it can kind of do the chimey thing if you turn the volume down, because it does have a treble bleed cap over it. If you turn the volume down and the master volume up, a little bit. of course, you have the low cut that you can use to get in the amount of girth you want. This is the neck pickup. And then, of course, this is the low cut all the way down. And then this is the low cut all the way up. So I tried to set the low cut such a place where if it's right up the middle, it's pretty good. The high cut is not really meant to be used other than to take the edge off if you want a darker sound for, say, like a jazz player or something like that. So here's the low cut in the middle position, and then I've got the high cut kind of just around the 11 o'clock position. Right, so it takes some of the edge off. Now, being that this has a cap over the volume knob, you can actually get this thing to warm up a little bit just by opening up the volume. I wish you could see it. I wish I had multiple camera views, but so I'm just turning the master volume down now. Kind of hear how it's just girthier. Right, so it's meant, this amplifier is designed to be more of a clean pedal platform amp. I didn't actually design it for the distortion. However, it does do the distortion thing. So let's put a distortion pedal on. So normally I would set this with the bass right around the 1 o'clock position and the high cut all the way up. And then I would set the drive for right around, yeah, just a little under noon. This is what the dude sounds like through it. So that's the dude. That's the dude in it. And then I've got another reverb and delay pedal that I stack after that. So you can tell it takes pedals pretty damn good. Obviously, it's meant to be a pedal platform amplifier, but you can, if you want. Some people like to get it right on the edge of distortion, right? So blow up the freaking gains here. So right around the 1 o'clock position is where you start to get the grit. I'd say that's probably right around where a lot of the, country guitarists might like it to be. As you start getting up to like the 2 to 3 o'clock, you start getting a little more of the grit, obviously. Now that is not power tube distortion, that is pi distortion. We are causing the pi to start breaking up now. So you can kind of, with the low cut knob, you can kind of get more of the AC 30-ish thing, that chimey thing going. And then of course, if you dime the volume all the way up, it just obviously just sounds a little bit grittier. You can obviously play with the low cut to dial in how much girth you want. So that's what this thing sounds like with the pi being spanked. Now what does it do if you put a boost pedal in it? I have here, this is just a clone copy. It's not exactly a clone copy. A clone copy. It's not very good clone copy, but it does something like it. But so you can hear how it just adds a little bit of grit to it. Obviously you can utilize that to get some of the distortion later on. So let me turn the torpedo back down and we'll turn the master volume back up. So right now the clone is off, right? This is all amp distortion that you're hearing now. So the pi is creating the majority of what you hear, and we're starting to get into power tube distortion. Sorry, I'm playing absolute bullshit because I don't want to have any copyright bullshit, so I'm literally playing just the cheesiest cheeseball shit I can possibly come up with. And I like freaking gritty, growly guitar shit like that anyway. But in your case, what does that sound like if we bring in the clone again? So this should give it a little more of that 80s grit that most people are used to. Sorry, I'm holding the guitar. I don't have a strap on right now. Shut up. I know what you're thinking. Anyway, obviously you can play with the master volume, and you notice that the fizz wasn't quite there yet, and it's because we have the master volume down, trying to keep it out of that zone. We're relying on the pi to get us most of that distortion, so... cleanup thing. So, you get it. This thing can do the clean to mean, and it takes pedals well. The problem is that when you've got the volumes dimed, it has the fizz. I don't like that amount of fizz. Now, here's an interesting thing. What I'm going to do is something that most people will tell you not to do. I am going to place the tap onto the 8 ohm tap. This is a 16 ohm load that I'm going into, and you'll notice that it goes away a little bit and it actually gets a little grittier. So you'll notice it changes the sound a little bit too. It kind of sucks the mids out a little bit. There's a little more balls, I guess, too, but it definitely kind of takes some of the mids out, which I don't really care for, but it does help a little bit with that fizz. Now, why is that? So another thing that kind of contributes to the fizz is the primary resistance of the output transformer. Now, the primary resistance of the output transformer is dependent upon the voltage that is on the plates of the tubes, believe it or not. And it changes where it sits. So if you were to measure the voltage at that point there, which is like 350 volts we were saying, at the thing, I can't remember exactly what the ratio is, but it's based on the wattage of your tube. We're going to interrupt this program to get some actual fucking data that is correct and on point, and kind of fill in some of the holes that I just fumbled about over. So going on to the primary impedance of an output transformer. Why is it important and why does it matter? Well, the tubes, the EL84 in this particular instance, have a desired range of primary impedance in which they like to work within, or that they are designed to work within. That range just ensures that they A, produce the amount of output that they are spec'd for, and B, just kind of helps protect the tube. When you start running it outside of those ranges, you can run into some problems. So how do you know what your actual primary impedance is? Question mark. It's not that number on the box. I have the box. So the output transformer that's in this particular amplifier says that its reflected primary impedance is 8,400 ohms. That is what it's supposed to be when you have the proper tap with the proper load. So with the 16 ohm tap plugged in with a 16 ohm speaker, you should have a primary impedance of 8,400 ohms. Well, how do you know for a fact that that's what it is? Because you can't measure it. It is a result. It is a reflective result. So if you change the tap, you know, the secondary impedance, it will change that load. And it's not a static load either. A speaker has an impedance curve, right? Kind of looks like a duck almost. So it goes up on the low end, dips down, and then it raises back up again at the high end. And it just happens to be that the nominal impedance of that speaker sits around 16 ohms. That's the DC resistance of the speaker, right? So the actual impedance that is reflected onto the tubes is a little bit different than just the nominal impedance, but that's all we can go by. So what we say is that with that particular load, a nominal impedance of 16 ohms, that it should be 8,400 ohms of primary resistance being reflected against the output tubes. But there is a way to tell more or less what you are actually reflecting onto those tubes. And to do that, you need to take the voltage that you have at your sender tap, which in this case is 351 volts. You need to times it by itself, so 351 times 351, and then you divide it by the max plate dissipation of the tube that you have. In the case of an EL84, it's 12 watts. What does that add up to? What does that look like? So we take 351 times 351, and then we divide that by 12. That gives us 10.266 kilo ohms. So we can say we have 10.2 kilo ohms of resistance being applied to the plates of the tubes. That's a little bit high. The ideal range for an EL84 is 8 to 10K. So you want to have at least 8 kilo ohms, but not much more, if not more than 10 kilo ohms worth of primary resistance being applied to the plates of the tubes. Well, we can already tell you that we're higher than that. We're at 10.2, which is, it's just barely higher. But what does that mean? What does the difference between 8 and 10K get you? Or I should say 8 and 10K get you. Well, as you go with a higher primary impedance, it actually causes the output tubes to break up sooner. So it lowers your headroom. It causes them to break up sooner, and you actually lose a little bit of output power. And it's because you were literally making that tube work harder to produce power. That's why it distorts more. When I put this thing on the 8 ohm tap, and you heard that and how it distorted more, it's because when I had the 16 ohm load, I was loading this down even more, maybe raising up the primary impedance to say like 12K or something, maybe even higher. So it causes that tube to work harder, distort more, and you heard the result. Now, what happens if you go the other direction? Well, let's say you get closer to 8 kilo ohms, right? Well, if you do that, you gain a little more, the amp will stay cleaner a little longer, and it will have a little more dynamic range because it stays cleaner longer, and it will also have a little more output. And it has a little more output because literally the the tubes have less resistance to push against, right? So what do we need to get in order to get, what voltage do we need at the center tap, or what B+ voltage do we need in order to get the voltage, the primary impedance down to that number there, the 8400 ohms. That'll tell us what our ideal voltage that we should be shooting for on this HT rail is. So remember I mentioned that I got it down to 300 volts, and it didn't fizz anymore, and I liked it. It was ideal, but it was too difficult to drop that amount of voltage. Trying to drop 50 volts was kind of difficult to do. What voltage do we need in order to get that ideal range? Well, one way that we can figure it out is to just keep punching in some numbers until we get there. But I've already kind of worked this out, so I know that it's about 317 volts. So if you took 317 times 317, and then you divide that by 12, you get 8,374 ohms. That's pretty much dead on to what we're looking for here. So ideally, we're looking for a we're looking for a B+ voltage of right around 315 to 320 volts, which is about 20 volts, 20 to 30 volts of where we're at currently. So we're a little high by about 20 to 30 volts. Now, remember I mentioned that the actual operating range of the tubes is supposed to be 300 volts. What would that get us? So if we were to have 300 volts, so 300, right at the design limitation, times 300 divided by 12, would mean that we'd have about a 7,500 kilo ohm resistance, primary impedance, going to the plates of the tubes. It's probably a little on the low side, but that would maximize the amount of clean headroom that you got. Now I can tell you that when I got it down to 300 volts, I think I got it down to literally like 298 sitting there, but I couldn't reliably do that. Doing so with the parts that I had would just be, the amp would only last a few months before it burned them parts up, so I couldn't send it out that way. But the amp got rid of all the fizz, so all of that fizz went away, and it sounded what I would consider to be better. But that's a subjective thing. Some people really like that fizz, some don't. But I would say that a safe number that I could reasonably get to would be to be able to drop that 30 to 40 volts. Now, what will that do with our operating range? That's going to change the bias of the amplifier. So you're kind of working out the difference. So this voltage here will adjust based on the actual biasing of the amp. So you're trying to find that happy medium. So by the time we get 320 volts here and have this thing biased at about 100%, I would say 95% of, dissipation, that would be the ideal place to get this amp operating at. The only real way I could think of to pull that off without having to get super crazy is to either use a custom transformer, like I mentioned multiple times you should, or we're going to have to Zener down our voltage a little bit. And there's a way I think I can do that where I can use 2 Zeners in 2 different spots and make it so that they're not working as hard, so that they're both not working quite as hard, which will allow me to get the voltage in the ideal spot and not have to worry about burning them up, in short order. So that is enough with this interruption. On with the regular program. Again, as I mentioned, this amp is really meant to be kind of a clean pedal platform amp. You take your Dude. I like the Dude. The Dude's a cool pedal. And it's especially better when you can actually fucking play right. Alright, I apologize. I know that it buzzes. So right now the guitar is just off. So what the hiss that you hear is just the hiss of the amp, which there is no hiss because it's not dimed. But let's see here. The Dude is currently off. This is how quiet the amp is. That hiss that you hear is the guitar off. This amp is dimed currently. The buzz that you hear is from the transformer. I can kind of prove that by just moving around. So obviously no shielding on this amp at all, and I'm standing literally a foot away from the amplifier, so that's not helping anything. And I have it turned all the way freaking up too. There, that's actually the volume that would normally be normal. But in either case, irrelevant, beside the point. This amp is very, very, very freaking quiet. So without anything on, and to give you another idea, if I were to mute the guitar amp, that's amp on, amp off, amp on, amp off. Very, very little noise. This is a very clean amp. So even with the heaters done up the way we've done them and all that other jazz, this amp is very, very, very quiet. So that's all we're trying to point out there. Very cool amp. It's definitely one of my better designs because it can kind of do a lot of those things. It does clean very well. It does the haunting cleans. It can kind of do the chime thing. It can do the country twang thing. And you can kind of get that, that Marshall grit and growl and all that jazz. You can get into shred territory with it with a little bit of help. It does require, a boost pedal or something like that to get into that. Obviously, I will get rid of the fizz. It can be fixed. We can get rid of that. That is not a problem. I'm just stating that this amp is affected by it, and we do have to mitigate it. But that is this amp. I hope you enjoyed this video series. I know it's a bunch of BSing, and you get this nice, wonderful static view here. Obviously, I need to redo some learning on my math or whatnot to figure out a couple things, but the concepts are there. You know that it can be done, and it does have an effect. Thank you so much for sticking with me as long as you have, and I hope to God that you like and subscribe and stick around and see some more, because there are more coming. Take care. We'll see you on the next one.